Syzygy, episode 101, Spin Down Earth. And welcome back. This is episode 101. This is Syzygy 101. It's like Syzygy for beginners. My name is Chris Stewart. I am in the office of Dr. Emily Brunsden at the University of York. Emily, hi, how you doing?
Hello.
It's good to be back. It's been a while.
It's been a while.
We had a return for episode 100 and then long gap. And listeners at home, you're wondering, what happened? You were back and then you were not back anymore. Life got in the way, didn't it, Emily?
Yeah, we got bombarded with this kind of succession of illnesses. So
it happens. Those of you who have children, you know. Those of you who don't have children, just imagine living with a large petri dish that just grows disease. And that's what having children is like. They're lovely petri dishes, cute and gurgly, and they smile every once in a while, and you get to watch them grow up. But they're still disease-ridden petri dishes. And I've got a 17-year-old and a 14-year-old, and they're still petri dishes. So you got decades of this ahead of you, Emily.
And the 1 week that I had off where no one in my family was ill that particular week, you decided to go walkabouts. So.
Yeah. We had that one little window and I went, sorry, I can't do it this time. So anyway, enough of the excuses. We're back. 101. We're definitely into the triple figures now. So this is good. What are we talking about today, Emily?
Well, so we're going to backdate a little bit because I originally did do my research for this.
This is an episode that we meant to do some weeks ago, but that's okay.
Yeah, in January, but it's okay. It's only March. It's fine. It's fine.
We're fine.
The science is still solid, or at least solid and liquid, as we'll find out.
See what you did there. So what are we talking about that is solid and liquid in the universe?
Well, I picked up this story. It was really interesting about how the rotation of the core of the Earth has recently been found to be slowing down to be less than the rotation of the surface of the Earth.
Right. Hang on. Okay, I've got questions. I've got a bunch of questions, but they can wait, right? That's where we're going today. We're going to be drilling down towards the center of the Earth and having a good poke around and going, what is down here? I mean, my first question is, Emily, I thought this was an astronomy podcast. But
yeah, we were going to drift a little bit. To be fair, some of the articles I read were in Nature Geoscience,
right,
which is new for me. But the word seismology was mentioned, so I got quite hooked.
Well, because that's your thing, really, isn't it? Astroseismology. So, cool. All right. That's where we're going. But before we do, stuff's been happening this week in the skies. If you've been anywhere near a dark and reasonably cloud-free area, far enough away from the equator, over the last week, and we're talking end of February while we're recording this, early March, then there's been a lot happening in the sky. In particular, some really pretty spectacular aurorae. Now, did you manage to see them?
No, not a chance.
No.
Remember, I've got an infant.
You've got an infant. So,
I go to bed before it's dark.
You could have been up in the wee hours of the morning and wandering around with a crying child, looked out the window and gone, look at the Northern Lights. Fantastic. Because, they were seriously visible across the entire UK, or most of it anyway. Normally, these things are visible, if you're lucky, up in Scotland, maybe the far, far north of England. But you normally don't get it as far south as York, and certainly not below that. But this week, it's been huge. Like, I've got an app on my phone that sends me alerts to say, there's a bit of there's a bit of space weather coming. There's a bit of auroral activity going on. You know, if you're in Scotland, you might be able to see it. And this week, it's just been pinging off the hook, saying, seriously, get outside, look up now, red alert. And there were reports coming in on the news on, I think it was the 27th of February, so just a few days ago, saying that people were getting really good sightings of the Northern Lights, like as far south as Cornwall, which is right down there in England. So we would have definitely seen it, except it was really cloudy because this is England. And of course it is. Of course it's really cloudy. But there were some great images. So, Emily, why? Why so much Northern Lights this week? What's been going on?
Well, this is called part of the whole sort of interplay between the sun and the earth. So aurora or northern lights come from charged particles that have left the sun, traveled all the way to the earth. They get funneled by the earth's magnetic fields. They start spiraling. So that's why they start to hit the poles of the earth, because they kind of preferentially bent round, funneled down to the north and south magnetic pole, but magnetic compass points, poles, that sort of thing. And that's why we get them in the very far north, very far south. And then when those charged particles hit the atmosphere, they can interact with things in the atmosphere, the nitrogen, the oxygen, for example. And as those atoms recombine, they let off lovely photons and greens and reds and all these lovely colours.
And the different colours come from different atoms and different molecules in the atmosphere, don't they?
That's right. Yeah. So nitrogen tends to be green, oxygen tends to be red, but you need to have quite bright aurora to be able to pick out the color. You can pick out the fact that there's glowy light shapes in the sky reasonably easily, because your eyes are sort of attuned to seeing bright versus dark reasonably well. To pick out the color, they need to be quite bright aurora.
Right.
But some of these ones that have been happening are.
This week it really has. And so, I mean, this is going on all the time, right? The sun is spitting out stuff that the Earth collects in its magnetic field and creates the northern and southern lights all the time. But sometimes it's bigger than others. And this week it's been particularly big. So why? I mean, has the sun been going a bit nuts? What's happening?
Yeah. So the sun has periods of sort of varying activity. It goes through periods of higher activity, periods of lower activity. And during periods of more or higher activity, it can release kind of bursts of charged particles. The very biggest ones you might have heard of are coronal mass ejections, where huge amounts of plasma is just kind of blown off the surface of the sun, causing this huge storm of charged particles, very dangerous for us, and particularly anyone who's unprotected by the Earth's atmosphere, namely astronauts.
Yeah, people up on the space station.
Yeah.
It's a bit of a concern.
But dangerous for satellites, dangerous even for power grids and so on Earth. But those are the very sort of big, enormous storms.
These are the ones that when you sometimes see images or videos from NASA. They've got these amazing cameras basically just pointing at the sun, and they capture these incredible images. But every once in a while they release one which is this enormous thing coming off the surface of the sun, reaching out huge distances, terrifyingly large eruptions from the surface. And am I right in thinking that if the timing of one of those is not great for us, if it's pointed right at us, that would really cause some problems?
Yeah, that would be bad.
Yes, on the scale of good to bad, that would be
quite bad.
Yeah. In the sense of,
you'd definitely lose a lot of communications. You'd lose your Wi-Fi. You'd lose things like satellite communications, GPS things, all those sorts of things, and potentially power in the big storms, because the charged particles start interrupting your power substations.
So that could really mess up the modern world.
Oh yes, that would make us unhappy. It
does kind of feel like it's just a matter of time then.
It is in some senses. These kind of big storms are relatively rare in themselves, and then for it to be pointing exactly at us is fairly unlikely. Yeah. But it's not impossible. Yeah.
But that's not what we're talking this week.
No,
this week is a step back from that, but it's still fairly impressive. Yeah. So was this a coronal mass ejection, or was this something else?
Just sort of a bit of intense activity from the sun. So we're talking a few steps down the ladder of big explosion wise. So lots of charged particles come in, but there's not any inherent danger at this point from this level of activity.
Right. And is the sun going through a particularly active period right now?
It's a good question. So the sun does have this cyclic pattern, which is about 11 years peak to peak. What that means is the sun gets kind of quite active for a period of 2 or 3 years, and then it calms down, and then that pattern repeats approximately every 11 years. Actually, during that whole time, the sun actually flips its north and south magnetic poles, which is quite an amazing feat, really.
That's, for something that big, there's interesting stuff happening in there. What's underneath that? What's happening down there? I mean, this is a whole episode in itself.
It is. But the crux of it is that the sun is not a solid object like the surface of the Earth, right? It's a seething mess of charged particles. And those charged particles are roaming around in the sun. When you have moving charged particles, you generate magnetic fields, and vice versa. Magnetic fields influence the motion of charged particles. So the whole magnetic charge sort of soupiness of the sun, it gets really messed up after a while because parts of the sun are rotating faster than other parts. It's all just a mess.
It's messy. As soon as you start getting magnetic fields in there, things are messy. I think that's a message that we've learned so far on this podcast about the universe. Magnetic fields equals messy.
So we had a really large peak. I remember in 2012 of solar activity where there was
11 years ago.
Loads of stuff. Yeah. And so we sort of have been we've been waiting for this period of more activity because this means more sunspots, more kind of interesting things happening in the sun. And when you run sort of degree programs where some of the laboratory exercises are things like measuring sunspots,
that's a nice thing.
It's helpful when they're around.
Yeah. Whereas sort of 5 years ago, it's like, well, let's talk about these things in theory, shall we? Because you're not going to see any.
Yeah, exactly.
Yeah. So does this mean we can expect more of the same coming up?
Probably. I mean, all the predictions are saying that we're probably not going to have a huge peak of solar activity this cycle. It looks like it's going to be a fairly modest cycle. But it has been climbing to maximum slower than we expected. The sun's, it's not a perfect 11-year cycle. It sort of varies a bit. And it seems like the sun's been a bit sleepy over the last sort of 18 months. So the climb to peak has been a little bit slow. But so it might climb a little bit more, or it might just start tapering off now. But it's a fairly low-key maximum, if that makes sense.
Yeah. All right. Well, I will keep the app on my phone, the one that's been pinging me all week saying, seriously, get outside, have a look. It's like, I can't, there's clouds. But if you listening at home want to keep your eye on potential aurora spotting opportunities, I'll put a link in the show notes to at least the app that I use, but other apps are available.
Yeah.
And it's worth, because I'd love to see. Have you ever seen the northern or the southern lights?
I'm one of the odd people who I've seen the southern lights, but not the northern lights.
Right.
Which is kind of odd because the southern lights are much harder to see than the northern lights.
Yeah. Although I would have thought New Zealand would have a reasonable shot. It's fairly south.
It's not that far south, though, really. I mean, we're much further north here in York than anywhere in New Zealand is south. So I was very lucky to be observing, and a fairly strong storm came through, and it happened to be quite strong for the southern part of the sky. So it was just a combination of events. I was very lucky to see it. I've only seen it twice, I think.
We shall have to see if we can collect the northern lights for you as well.
So one day I will get there as well.
Good. Right. On to topic du jour. That was just a little aside because it's happening like literally right now. But we're going to turn our sights from looking upwards at an aurora to looking downwards, which is confusing to me, as I mentioned, Emily, because I thought this was an astronomy podcast, but we're going to look towards the core of the Earth. So why are we doing this?
Yeah.
What's going on?
Well, there is a nice link, actually, between what we've just been talking about and what we're going to talk about. And that is, of course, the magnetic field of the Earth.
Right.
So the magnetic field of the Earth is responsible for protecting us from the bulk of these solar storms, these charged particles. And, of course, that's also responsible for spiraling in a few of these particles at the pole, creating the aurorae. But where does that magnetic field actually come from?
That's a really good question. I like it, and I'm glad we're tackling it because it's one of those things about our planet. And I mean, okay, here's astronomy question first out of the gate. Do other planets have magnetic fields?
Only Jupiter has a really strong magnetic field.
Really?
Jupiter's is much stronger than ours.
Of all the ones in the solar system, it's us and Jupiter.
And Saturn has a bit as well, but not as strong as Jupiter. Yeah.
Okay.
I think the others do have a little residual one, for example. But most of them are so tiny that they're not worth talking about.
But it's one of the things which is kind of, you learn very early on in your childhood experience of the world that the Earth has a magnetic field. How do we know that? Well, because we have compasses. We can point north because we have a little thing which has an arrow on it that says it's that way. How do we know that? Well, because we have a magnetic field. But the more you think about it, the more you think, that's just magic, isn't it? Surely, that can't be right.
Well, every textbook for children has this picture of the Earth with a cutaway, and then there's a big bar magnet in the centre of it, right?
Yeah, which isn't.
Who put that there?
There isn't a big bar magnet with a north and a south written on it, is there?
No.
Okay, so what is down there? Why don't we tackle that first.
Yep.
What is it?
Well, the simple answer is that we've got a liquid part of the core of the Earth that therefore has charged particles in it. Charged particles, moving magnetic field.
Okay.
Same thing as the sun.
Right. So that's some basic electromagnetic physics going on there. And by basic, I mean actually really complex, because it always is. See previous comment about magnetic fields. It's all messy. But if you have moving charges, you produce a magnetic field. And a changing magnetic field can move charges around. And so that's the link between electricity and magnetism that gives us electromagnetism in the theory. So if we've got moving charges down there in the core, then we have magnetic field for free.
Yeah.
That's what physics does for us, folks. Good.
Exactly.
So that's where that comes from. Great.
So let's look at the structure of the Earth to see
Cool.
where that kind of all fits in. So I've decided to work in diameters today. I'm not really sure why I chose diameters.
Okay.
I would normally work in radius of the Earth, but just work with me here.
All
I'm
right,
going with
all right.
diameters.
Let's go with it.
Okay, this whole Earth is a ball, roughly, right?
Sure.
Which is about 12.8 thousand kilometers in diameter.
All right.
So across.
Anyone wanting to work in radii, just divide everything Emily says by 2.
Yeah. It might make more sense. I don't know. We'll see by the end. Now, on the surface of that ball is the crust, and that's the bit that we live on. It's somewhere between 5 and 70 kilometers thick.
Okay, hang on. You said about 12, did you say 12,500 kilometers across? Yeah. And we're on a tiny little crust, which is how thick?
5 to 70 kilometers.
That's nothing.
It's nothing, yeah.
We kind of think that we're on the really solid bit, and actually it's just this really thin layer on top. That's nuts.
So, yeah, every diagram that you've seen showing the crust with some width is actually wrong.
No, you wouldn't see it on that scale.
Exactly.
Good, right.
But anyway, that's the bit that we're, I guess, living on. But what's underneath that crust then is the mantle, and this is kind of just liquid rock. I'm not a geophysicist, but I think it's a good, simplification that it's just melted, gooey rock.
To first order, we're floating around on a layer of crust of solid stuff which is floating on liquid rock.
Yeah.
Not far down.
No, not that far down. Wow. And in some places very close to the surface, and we get volcanoes and bits of lava just coming up. Yeah, exactly. Bits of the mantle trying to escape. So that's the mantle, and that's it's liquid because it's hot, and there's all sorts of interesting things about the mantle that we're not going to go into today. But what we are going to look at is the core of the Earth. So the whole core is something like 7,000 kilometers across. So 7 out of 12 and a bit.
So it's a lot. The core, like when I think of core, I imagine a very small little bit down the middle. But when we talk about the core of the Earth, it's actually a large chunk of the entire sphere.
Yeah.
Yeah. Okay.
Yeah. Now, we take that core, there's an inner bit and an outer bit. The inner bit is only 2.4 thousand kilometers, 2,500-ish.
Okay. Still a sizable
across.
chunk. Yeah.
Yeah. Now, that's the solid iron bit.
Right. And we're sure of that. Like, I can remember discussions not that long ago, not between us, but just, reading about them, where still not entirely sure what's down there. But we're sure. Center of the Earth, solid iron.
Yeah, to first approximation, we're sure. I mean, there are some subtleties.
Such a good statement. It's like, sure. Yeah, why not?
Roughly.
We know this. Asterisk. Yeah.
Ish. I mean, well, we know that it's solid. We know that it's mostly iron. I mean, what the exact chemical composition is being looked at, obviously. And there are subtleties about the structure of that core. But for the broad brush approach that we're going with here, especially because, as I say, geophysics is not my strength.
We won't delve too much into your depth of knowledge.
It's a solid lump of iron.
Sure. We'll take that as read.
Yeah. So that little lump, that lump of iron, is suspended in a way in the entire core. So you've got the 2,500 kilometers out of 7,000. The rest of that 7,000 is a liquidy version of the iron core. It's got lots of iron, bit of nickel perhaps in there, but generally a liquid version. And there's a boundary where the solid meets the liquid, where it's crystallizing. So actually the Earth's core is cooling slowly as time goes on, which means you get crystallization. So the solid bit's growing over time.
Right. So some of the hotter liquid bit is crystallizing out, and the ball in the middle, the solid bit, is slowly growing.
Yeah.
Cooling and growing.
Yeah.
Okay.
But that sort of ball is suspended in the liquidy bit. So it can rotate independent of whatever's happening with the rest of the Earth, in a sense. So we know that the Earth itself rotates, right? Here's a good question. What is the period of rotation of the Earth?
Period of rotation. Well, the Earth spins once a day. Is this a trick question?
A little bit. It is a little bit of a trick question.
Yeah, once a day.
So
period of rotation of 1 day by definition.
Ish. Depending on how you're defining it.
Right. Okay.
Actually, so we would say it's 24 hours, which is called a solar day. And that's the time that it takes the Earth to turn such that the sun returns to the same point in the sky, right?
But is the catch that we've now moved a bit in our orbit? So we've actually gone a little bit further.
Yeah.
We've turned a little bit more.
Yes.
Okay.
Yes.
So it's if you pick a spot in space, right, to ignoring the movement through space, which I'm assuming is a bit slower, that star, right, we're pointing at that star right now. How long until that star comes back into the same spot in the sky? Slightly less than 24 hours.
Exactly. 23 hours, 56 minutes and 4 seconds.
Right, slightly, not a lot.
4 minutes.
Okay,
well,
cool.
I mean, if you talk about the length of a day, 4 minutes could be quite important.
Yeah, that'll build up.
But we call that a stellar day or a sidereal day.
Okay.
So that's actually, if you ignored everything else that was going on in the solar system, if you said, how long does the Earth take to spin once on its axis, that would actually be that 23 hours, 56 minutes.
Okay.
So that's how long it takes the surface of the Earth to rotate round once, right? The rotation of the core the period is similar, but it is very subtly not exactly the same.
Right.
And it appears that at some points in time, and I say not even in deep, dark, mysterious time, like literally in the last 70 years, at some points it's been spinning faster than the surface of the Earth, and at some points it's been spinning slower than the surface of the Earth.
And is that, I could imagine 70 years ago, right, it was spinning faster and now it's spinning slower, and what you just said could be true. But you could also interpret what you said as it was slower, it got faster, it got slower again. Like it's changing. It's not just slowing down, it's changing up and down.
It seems to be the latter. It's changing up and down. Wow. Yeah,
okay.
Really
so
exciting.
That's weird, right? Because that implies a cause. I mean, they both imply a cause, but I can imagine something slowing in the same way that the core is cooling, right? You said it's cooling, it's growing. And if you said in that same breath, and it's slowing, fine. That makes sense to me. I can see all of those things coming together. But if it's changing, it's speeding up, slowing down different times, why? Why would it do that?
It's a good question. We don't know.
Okay, good.
There's different timescales going on here. So I talked about cooling and getting bigger. That timescale of that process is massive, right? That's your billions of years timescale of growth of the core. So let's just put that thought aside. Forget I even said that.
Okay.
For the purposes of the last 70 years, that process is completely irrelevant.
That's very, very marginal. We'll ignore that for the time being.
Yeah.
Forget it. That's not happening.
But what we have measured, and this is what the paper, the kind of headline of the paper is that...
We should probably establish who. Who are we talking about? Who's done this?
Yes. So this is a team that's led by Yang and Song. So this was the January 2023 paper that came out. And they've measured that the rotation period of the core got up to something like 1/10 of a degree faster, or it turned 1/10 of a degree more over the course of a year than the surface did. Mm-hmm. So it went a little bit further. Not by much. 1/10 of a degree is not much over a year.
It's not much, but it's there.
Yeah. And it did that for a while. And then sometime in around about 2009, the two periods matched. Mm-hmm. And then since then, it seems like it's slowed down.
Right.
So it's now going slower than the surface.
Why? Why? What's going on?
Well, we don't exactly know. There's a lot of intricacies in the actual, I guess, the way that the Earth's core is rotating. I mean, it depends on the local thicknesses. I mean, everything's not particularly exactly spherical. You've got different densities of material. You've probably got some kind of wobbles that are coming in from the fact that the Earth itself wobbles as it goes around.
Yeah, I mean, the Earth
like
is
all sorts of weird things.
It's not a perfect sphere. and it's not behaving in a perfect sphere, rotating in a perfect way kind of way. Like it does wobble, doesn't it? It's sort of, what's it called? There's a word for the wobble.
The precession.
That's the one.
Yeah.
Yeah, it has precession. It precesses. It wobbles around as it goes. And I guess that kind of shakes things up a bit.
Yeah. So the point of the research isn't really offering up an explanation for this because actually we're still at the point of trying to determine, is this a real effect? we'll work on the why later.
Sure.
Let's just make sure
Let's nail this down first.
Yeah. So what they're doing, and this is where the seismology jumps in, is really interesting, is they're taking measurements of kind of earthquakes, but not like big, devastating, once-in-a-decade earthquakes that we unfortunately have been seeing, but little periodic earthquakes that just seem to happen relatively regularly, just from little inconsistencies in the way that, say, two tectonic plates rub against each other.
Yeah, I mean, this is happening all the time.
Yeah.
There are little earthquakes happening all the time. We just don't notice them.
Exactly.
Which is a good thing.
Yeah. So these are kind of your predictable, like, background level earthquakes. But you can detect them not only from just one measuring sort of station close to where the earthquake is happening, you can detect them from other measuring stations all over the world. And so by looking at those and looking at how those seismic waves have traveled through the rest of the Earth to get, and the timing of that travel to get from one end of the Earth to the other, or through the middle of the Earth, you can therefore determine the rotation rate of the core.
I mean, that is extraordinary, right? That I would have thought. I mean, sure, you step back far enough, the Earth is a perfect ball, but it's really not. It's really not. You can tell there's lots of wet stuff on the surface, interrupted by bits of dry stuff with big mountains and stuff on it. And all of these bits are moving around. Like, it's not a simple thing. And so when one part of it rubs against another part and goes, earthquake, sure, I can see how you could measure that nearby and on the other side of the world. And I could see how you could learn something about how those earthquake vibrations, the waves, bounce around the surface and through the middle. But that seems to me really noisy data. Like, it's amazing that you could take that and go, and therefore the core is rotating like this.
But doesn't all this sound hauntingly familiar? I mean, this is why I picked up this story, right?
It's beginning to sound a little bit like some other systems that we have talked about in the past.
Exactly. Yeah. Some of the stars that I've studied, we look at the pulsations on the surface of the star. Okay, they're much bigger than earthquakes. They're actually large scale changes in the surface. But the whole principle is the same. The seismic waves move through the interior of the star. They therefore capture the information about the interior based on travel time, etc., and therefore tell us about things like the rotation of a core of a star.
Which, like, you're not dispelling the fact that I still find that absolutely gobsmacking amazing, because it shouldn't be possible. And equally so, or more so, for stars, because at least here on Earth, you can whack a box down on the ground and go, here you go, measure that. And you can put another one on the other side of the planet. Like, you can't do that with a star. So I'm calling here on Earth, measuring the rotation of the core of the Earth, that's ridiculous, and well done for being able to do it. You people measuring the cores of stars, no. Like, no, you're making this up. This can't be possible. How are you doing that?
Well, no, it's just these pulsations are traveling through the media and they bring that information with them to the surface, which is brilliant. And to be fair, I think we're about as confused as the seismologists here, because we're getting stars that some of the stars of the same type that should be behaving in very similar ways, but some of them seem to have cores that rotate faster than the surface. Some of them seem to have cores that rotate slower than the surface. We don't know why.
So
that's a big question mark that we're dealing with.
So the idea here seems to be the core can rotate.
Yeah.
And it might be faster or it might be slower, but you're not going to know until you measure it. Okay, question. Like, I'd said it facetiously a minute ago, but seriously, and I know we have talked about this before, but it was a while ago. Hell, it's been a while since we did episode 100. So, I'm not remembering these things. As I said, here on Earth, you can put a box down on the surface of the Earth, and it is literally measuring vibrations of the Earth. How are you measuring the equivalent of a star? What are you looking at that gives you the information about the core? You're presumably just measuring the light coming from the star.
Measuring the light, yes.
But what in the light?
So when you look at a pulsation on the surface of a star, you can look at it in generally one of two ways, or both ways if you're doing very well. You can look at the changes in the brightness of the star, which tells you how the surface is changing. So you can look at waves traveling across the surface of the star. They change the brightness of the star. So our wonderful precision space telescopes like Kepler and TESS are just perfect for this kind of stuff. So they're measuring the brightness changes, which tells you the pulsations, which you then analyze and figure out, well, those pulsations traveled from here to there.
Okay, I've got my hand up again.
Yeah.
Okay. Again, I'm sorry, it's going to take me a little while to catch up on this. You can see, if you were looking at the sun, right? The sun has a size in the sky, and I can see how you could look at that and go, different parts of that are lighting up in different ways, and we can see the brightness of the sun. Like the brightness of the sun is it's not a dot. It's a disc, and it's a rotating disc. We can see different parts of that. The stars that you're looking at, even with the best telescopes, are still dots.
Yes.
Right? And so you are extracting information about quite complicated vibration and oscillation patterns of a star from changes in the brightness of a single dot in the sky. Am I right?
Yeah, I didn't say it was easy.
Like, that's insane. You can't do that. How?
We're going down to, changes at least in 1 part per 1,000, usually smaller.
Episode 101 of Syzygy, in which Chris's brain explodes. I mean, that's just, I can't imagine how you extract that data. That just feels wrong, impossible. Ridiculous.
Well, yeah, I mean, it's only in the last sort of 40 years that we've been really able to do this with any kind of systematic precision. So we're very lucky that we can measure these. These are larger scale oscillations. We're not. The sun does have these kind of oscillations, but they're a different kettle of fish, if you like. They're much smaller, the ones that we see on the sun. So we are looking at much larger versions of pulsations, to be fair.
Right. Okay.
But they still cause very, very tiny changes.
Yeah. And then from that, you can extrapolate to, well, if this is happening, then something, we can infer what's happening down inside the core, even from those really subtle changes in brightness of a dot in the sky. You're able to make those inferences.
Yeah, because if you're really lucky, you have not just only the changes in the brightness of the star, you can also measure the change in the velocity of the surface of the star, which is my forte, if you like. I work in both, but I prefer. I'm really a spectroscopist deep down inside, which means that I do prefer to look at the Doppler shift of the star. And when you look at the Doppler shift, you can actually take what starts off as a point of light, you can actually turn it back into a disk.
Right. So you can see, okay, backing up a little bit, Doppler shift, for those who haven't remembered from when they studied this at school, or if you never studied at school, that's the car driving past kind of thing, where the sound coming from a car as it comes towards you sounds higher, and as it passes you, that pitch of the sound drops as it's going away from you. As it's coming towards you, the waves pile up, and so it makes a higher frequency. As the car's gone past you, the sound waves spread out because they're driving away from you, and that makes a lower frequency. So that's what we call the Doppler shift of that sound, from high to low as the car passes. Same happens with light, right?
Yep.
If something is emitting light and it's coming towards you, the thing itself that's emitting it is coming towards you, then those light waves will bunch up a bit and make a higher frequency of light, which is a bluer shift. And if the thing that's emitting the light is going away from you, then the waves spread out a bit, and that makes a redder shift in the frequency of the light. Okay.
Yep.
So that's Doppler.
Yeah.
You're talking about, am I right, that as a star rotates, one side of it, if you're looking at it, is coming towards you.
Yep.
And one side of it is going away from you.
Yep.
And so one side will be blue shifted and one side will be red shifted.
Yep.
And you can measure that.
That you can measure. That's fairly straightforward. That's the easy bit, actually.
Again, just clarifying, this is from a dot.
Yes.
So you're seeing in the light from that dot, at the same time, in the same place, a little bit of red shifted and a little bit of blue shifted, and that tells you how it's spinning.
Mm-hmm.
Okay.
And then on top of that, you've got the pulsation. Yep. So the pulsation causes a part of the surface to move towards you and a part to move away from you. So at the blue shifted bit of the star, so the half that's moving towards you, could have 3 big pulsational waves on it that are coming towards you and going away from you. So you get that extra information layered on top of the information from the rotation.
I've got so much respect for your research field now. Not that I didn't before. I'm not sure that it had quite sunk in. Okay, good.
So yeah, it's beautiful. You can pick out all these waves and you can look at how those waves are interacting with one another. And it's actually the interaction between the waves themselves that tell you what they've experienced, I guess, as they've traveled through the interior of the star.
Wow. So is there anything that the Earth's core people and the star core people can, share? Can you give them any hints?
That's a good question. Probably not, really. No. I think what the seismologists are looking at are quite different types of waves. They're looking at much more sporadic sets of waves. I mean, the Earth doesn't pulsate in a nice regular way. I'm sure they'd love it if it did. It might make seismologists' jobs a bit easier. But I don't think there's anything direct, apart from a lot of sympathy for how hard this actually is from one community to another.
So basically that would be a really short conference of the, the combined, stellar seismologists and the Earth seismologists going, yeah, hard, isn't it?
Mm-hmm.
Well, anyone for a drink?
Yep.
Yeah, that's basically it.
I think that would be it.
So coming back to where we started, we had a little detour off there where Chris's head exploded.
Yeah, an unexpected astroseismology lecture.
Yeah, but I mean, that's okay. It's syzygy, right? So coming back down to Earth, literally, and looking back down at that core, you said something like a 70-year period that we've been looking at here. So
yeah, well, this is the interesting thing. So we've been seismology has been measuring vibrations in the Earth for decades, if not more than 100 years. So we've got a reasonable, at least the last 50 to 70 years as a reasonable data set. And some of that's being reanalyzed now. There was some interesting work done in 2022 by the same authors of this more recent paper, where they looked at declassified information from the US military about nuclear blasts that they did in the kind of late 60s, early 70s. And they were able to look at some of the seismology of those blast waves traveling through the Earth, which is...
I mean, look, positive benefit of nuclear testing.
Yeah.
Who knew that would be a thing? But
and it was at that point that they realized that the Earth the core had this sub-rotation. So at least in that sort of 69, 71 period, the Earth's core was rotating slower than the surface. I mean, that's not that long ago. That's within many people's lifetimes.
Yeah.
Right?
Yeah. I mean, that's the beginning of my lifetime.
Yeah.
No comments, thank you.
So the Earth was rotating, the core was rotating slower than the surface at that point. And then at some point from 1971 onwards, it sped up. And then the latest paper has been looking at the region of time between 1995 and 2021 using the seismology. And then at some point in around about 2009, we've had this flip over. So it's gone from being faster. We don't know when it got faster between 71 and 95, somewhere in there.
Sure.
Some point.
But again, that's not a long period of time, like a couple of decades.
Yeah. Some point in there it got faster. And then in 2009, it's crossed that boundary back down again.
Slowed down again.
Yeah.
Very weird.
It's
But I mean, it's a classic example. Like, we think we know so much, right? As a species. In 2023, like, we got a lot worked out, right? But there are some things which we've only really just scratched the surface of. And this is one where we haven't known about this as a thing for long enough to be able to spot the patterns yet. You know, it's a little bit like, it's amazing to think that we only really figured out the whole tectonic plate thing, like within the last 100 years. Like that's
the concept
ridiculous.
of a galaxy is only 100 years old.
Yeah, like we've got so much catching up to do.
Yeah,
and
amazing, isn't it?
Here's another one, which is, so it turns out that the rotation of the Earth's core, it's complex, and it's complex over a time scale of as long as we've been looking at it. Like, we haven't had enough time yet to figure out what's going on, that's wild.
It's weird, isn't it?
Yeah.
So there's some proposal that it could be kind of a 70-year oscillation-ish. I don't know.
But is that because we've been watching it for 70 years?
That seems to be it. So
it turns out it's 80 years, not 90, 100 years, 110 years.
Or it could just be a bit more random than that. There could be
Sure.
some more sort of fluctuating stuff.
Yeah,
So
I mean,
I
maybe
think
there's no pattern at all.
exactly. So that part I think is debated for good reasons. But it's just going to be a matter of watch this space and see what happens over the next, say, 70 years.
Yeah, I mean, who would have thought that such a crazy mixture of stuff down in there with, like, even just thinking about that boundary. And I know that you said it's over, really long time scales, but that crystallization boundary, that doesn't sound like a simple, nice, shiny, solid sphere rotating in a nice, well-behaved liquid. There's some complex fluid dynamics happening in there, and thermodynamics and all sorts of stuff.
And magnetohydrodynamics.
And that's not even bringing in the magnetic fields, which, let's face it, they're the worst part. So who would have thought that might produce potentially some really complex behavior? Wow. Yeah, that's fun. So, Emily, what does this all mean? Can we extract any meaning from this, or is it firmly sitting in the category of, well, there you go. That's a thing.
It does matter. In fact, it matters, I think, very directly in ways that often we would struggle to make the connection with in terms of astrophysics.
Okay.
I mean, this is our planet, right? So it's quite easy to draw some very direct conclusions for us. A big one is the change in the Earth's magnetic field. So Earth's magnetic field is driven by this, what's called geodynamo. So the movement of this liquidy core basically is driving our own magnetic field of the planet. So if that changes, then the strength of the Earth's magnetic field and possibly even the directionality of it could subtly change.
You do hear, subtly, you do hear every once in a while of a big report which is the sort of thing which will then make headlines, which is, oh my God, sometime within the next insert number of years here, the Earth's magnetic field is going to flip. Is this related to that at all? Like you hear
I don't
that from
think
time to
so.
time?
No, I think this is more about the subtle changes in the strength and potentially subtle changes in the actual. So the location of the North Pole, the geomagnetic North Pole shifts anyway, right?
And shifts like by significant amounts.
Yeah, by meters, right?
Yeah.
So at least you're hunting around on the ice field of wherever you are
Where
in the North
did we
or South
leave
Pole.
that pole?
Yeah, exactly. You've got to kind of keep moving your flag around a little bit.
But I mean, over longer time periods, it's shifted by a hell of a lot more than just meters. Like I've seen maps where it's sort of, dipping down into northern Canada and stuff, and it sort of wanders all over the place.
Yeah. So part of that is precession of the Earth as well.
Right.
But yeah, there's lots of bits that contribute to that. And this is one of those components that will contribute to those things. And of course, the strength of the Earth's magnetic field does matter because, we are being protected from those solar storms.
It's not just about finding your way around. It's not being killed by cosmic radiation or solar radiation. Yeah.
It also affects things like the rotation period of the Earth itself. So we talked about a solar day and a sidereal day. What's happening here is that the changes in the core can make the length of the day change. So at the moment, the length of the day has changed to be a bit longer than it was. In fact, it's looking at the overall rotation of the Earth. We're looking at something like 1.7 milliseconds longer day than 100 years ago.
It's not a big effect.
It doesn't sound like a lot, but over time, those kind of effects do matter because they impact, for example, how many hours of daylight a particular region would have, which influences temperature, influences climate, right? If you're pouring more sunlight onto your ice caps, then they may not be able to remain ice caps. These are the long-term, long-term
Sure.
shifts.
I'm guessing that the climate has bigger influences right now. That's one of the smaller ones.
Well, yeah, maybe. But there are some big questions about how the Earth's magnetic field generally affects the climate and how changes in the magnetic field may have driven large-scale climate changes over the last billion years or so.
Sure.
There are some interesting questions there, I think, to think about as well. So it's important. It is important to know these things about our little home.
But the first step, I guess, in this research is it actually happening or not? And do we have, like, is it confirmed enough to be able to put a big stamp on it and say, this is definitely what's been happening? Are other people able to back it up, or is it big question mark still?
I think it looks the data look very good. I mean, I don't think there's general kind of overall debate as to whether or not there is some change in the rotation rate of the Earth's core. I think the fact that it's changing has been by consensus accepted by the expert community, not necessarily myself. What exactly that cyclic nature of that, I think, and what potentially might be the cause of that are things that are still being, hashed out. But the fact it's changing, I think, is pretty obvious.
Big questions still to be answered.
Now, just as a last little aside, since we're talking about the core, now we put a little pin in the whiteboard, my beautifully, magnificently clean whiteboard at the moment.
Like, long-term listeners will know that the whiteboard in Emily's office has been a staple for this podcast. It's a really important part of what we do. And I'm looking across the office and the whiteboard is empty, Emily. This is kind of freaking me out a little bit.
It is a little bit scary to see a scientist whiteboard empty.
We have no topics. We have no equations, nothing. It's almost like you've been away for a while.
I did have a little bit of a clean. Don't worry, I do have a record of all the syzygy topics that were on the whiteboard.
I seem to remember we did take a photo of it, actually.
Yes, yeah.
Anyway, point is, at one point, there was a dot point on there, which was something about the core?
Yep. And turns out that the core is actually younger than the surface of the Earth.
Okay, insert long pause here while Chris tries to pass what Emily just said. What? Sorry. As in it was formed later?
No, it was formed, well, at least slightly earlier, if not pretty much at the same time as the rest of the...
It's the middle part.
Yeah.
It's not like there was a hole there and then something dropped into it. It's the middle of the Earth. So, what?
It turns
out
out
that... younger. That doesn't make any sense.
It's weird, isn't it? So it turns out the core is actually aging slower than the surface.
Core is aging... Oh, is this an Einstein thing?
Oh, yes.
Is this a relativity thing?
Oh, yes.
Okay, hang on. I'm going to see if I can figure this one out. Einstein said that the faster something... Well, when things are moving at different speeds, time goes at different rates for them. Time is relative. Okay, so that was one thing, which is weird. It's weird enough in and of itself. But Einstein also then went further and said, hold my beer. That's not weird enough. Do you know what else is weird? Gravity affects time too. Gravity is warped space-time. And so when you've got a lot of mass or energy, like, say, a planet, then that warps, it bends the space-time in the vicinity so that when you are closer to a large, massive object, time is going at a different rate to when you're further away from a big, massive object. So down towards the center of the Earth, gravity is going to be a bit different to the surface of the Earth, which means time will be moving at a different rate.
So if you have a clock and you have it running on the surface of the Earth and you took an identical clock and took it to the center of the Earth, it's not a good idea because the center of the Earth's a horrible place, but
but in principle, one of those great Einsteinian thought experiments.
Yep, you're basically in the middle of a deep gravitational potential well. There's lots of gravity effectively at the center of the Earth, so your clock will run slower.
So that means that all the stuff down there, I mean, how do you even think this statement through? All the stuff down there is literally slightly younger than the stuff out here, even though it all started at the same time.
Yeah. It's great, isn't it? And the Earth's been around long enough that this change in the passage of time that's perceived by, say, a lump of iron at the center of the Earth compared to a lump of iron on the surface of the Earth means that the lump of iron at the center of the Earth is about 2.5 years younger.
2.5 years? Oh my God, that's insane. I mean, this is straight out of Interstellar, right? You've seen the movie Interstellar, where they go to the planet that's orbiting the black hole.
Yeah, we won't talk about going in the black hole bit, though.
No, well, that's just weird. The first half of Interstellar, where it makes some kind of sense.
Yeah.
Although, I mean, my question about the planet that they went to that's going around the black hole is, why is it light on the planet? Like it's just like Earth daylight. That wouldn't. There might be a lot of light around, but I don't think it's... Anyway, put that aside. The point that I'm getting at is that when they go down to that planet, they have to be as fast as they can because time is going at a very, very different rate because you're closer to this stonking great black hole, huge amounts of gravity, right? Whereas back on the original spaceship, time is going at a very different rate. And so an hour down on the planet is like 30 years or something back on the spaceship.
Yeah.
And when they get back, the dude that they left behind is like much older and surprisingly doesn't immediately want to just kill them all because he's been up there waiting for so long for these guys to get back. Anyway, is it same idea?
Yeah, exactly the same. Yep.
Wow. Couple of hours.
Yeah.
That's nuts.
So
like
2.5
relativity
years.
is mad.
2.5 years, yeah.
Cool.
It is cool. I mean, you can ask the question, does this matter? Again.
Sure.
There are two ways to answer that. The first way is not a bit. It doesn't matter.
Not even slightly.
No.
Does this affect us? No.
No. Do we care? Does it matter when we're studying the rotation of the core? No.
Do you have to factor that into your equations when you're doing all your seismology stuff? No.
Probably not. No. However, the answer is also yes.
It does matter.
It does matter because in some instances we try and do things incredibly precisely.
Yeah.
And one of those instances is when we do things like GPS.
Yes.
GPS is amazing. I don't know if you remember, but when certainly the first time I used GPS would have been, I don't know, in the late 1990s, I think, probably. I was on a boat.
Much earlier than I was. I didn't use GPS until I actually got a, suitably up-to-date phone.
Well, I was on a boat. I think it was a houseboat even. And we were sort of floating around in this harbour. We hired this houseboat for a week. And it had a GPS on board to, obviously tell you where you were in relation to the rest of the harbour. Now, I remember that GPS being so rubbish that we were about 100 metres that way, which meant we were on top of a hill.
Yeah.
In the houseboat.
Which, for a houseboat, like that kind of error is important.
Yeah. So we clearly weren't. So I remember thinking, this GPS malarkey, whatever. Doesn't
nonsense.
Work. Yeah. Now, the thing is, to do GPS properly, you actually need to include general relativity because GPS satellites are further off the surface than we are. Therefore, time passes very, very slightly slower again for those GPS satellites. So they need to make the correction back so that when they are calculating time and then getting precision locations on the surface of the Earth, they're not going to be 100 meters off. You can get down to your few centimeters, which is the norm today, right?
Yeah, which is like, it's amazing. But that's, people talk about relativity being a very small effect. But when you're talking about that level of precision, turns out you actually have to do the general relativity calculations. That Newton's not good enough anymore if you want to get to within meters of your actual position on the surface of the Earth, which is... That's wild, right?
Yeah.
That's
and you
really
think
cool.
about how many thousands of applications we have now for global positioning, right?
It's just commonplace.
Yeah, everything from sport to just looking at where your aeroplane currently is when you're flying over the Indian Ocean. I mean, there's loads of it's just part of everyday life.
Yeah.
So general relativity is part of just everyday life now.
Yeah.
Does it matter? Yeah, in some ways.
Yeah, it kind of does. I mean, maybe not specifically for the Earth's core. Jury's still out on that, although you never know. It might come up in the future. But certainly those kinds of effects, measurable effects of general relativistic stuff, we use it constantly, all the time.
So you can feel very clever now knowing that in your pocket is a device which is actually taking into account general relativity as you walk along.
Well done. Well done, everyone. Well, Emily, finding our way out of this episode, I'm feeling really good about a whole bunch of things right now. I'm feeling good that I've got a device in my pocket that measures general relativity. I mean, implicitly. It's all built into the GPS system, but that's kind of cool, right?
Very cool.
You should feel really good about the fact that you're working in a field of astrophysics which is bananas and shouldn't be possible, and yet it is. And so, well done you and all of your colleagues. I think that's awesome. But in particular, we managed to do an entire episode of Syzygy looking downwards rather than upwards. And that's that's kind of special.
It's very
I
cool.
think.
Yeah, we dabbled in our own little bit of geoscience.
Yeah. So look, it's really nice to, we've said this a few times over the last couple of months, it's nice to be back. We're going to continue trying to be back, but back is a fairly random thing right now. So who knows when the next episode will be.
Oh, please, I couldn't do with another flu. I've done enough of them.
No, enough with the viruses already. Well, we'll see what we can figure out. In the meantime, being back, we should probably address one of the elephants in the room, which is the elephant of social media. Emily, are we still on? Does social media still exist in 2023? Is it a thing?
I think it might be.
I think it might be. Twitter is a big of a question.
Yeah, it's a big question mark at the moment. So
Yeah.
we'll update you in future on that one.
Yeah. But I mean, we are still out there. If you want to go and find us, we are on the Instagrams
Yes.
at SyzygyPod.
Yes.
Is still a thing. We are on Twitter, same handle.
Yep.
At
We'll
SyzygyPod.
eventually have a look at it and see what we can figure out.
We will get there. As soon as we can beat all of these viruses, we're done. Like, we're good. And where else?
Well, our website is always the
course.
go-to, right? No matter what's happening in the controversies of the social media world, we will always have this beautiful website
We'll always have
with
the
a
website.
lovely little box that you can write what you think and send it to us.
Yeah. And what is that website, Emily? Remind us all again.
Syzygy.fm.
That's the one. All of the past
SYZYGY.
all of the past episodes, all of the details, everything you could possibly need to keep your syzygy habit going. So, yeah, we'll be back. Look, let's say for the sake of an argument, in a week.
We're booked in for next week.
We are booked in. Listeners, you may not believe this, but we do have a standing calendar appointment for a syzygy recording every week. Like, legitimately, we really do. So, on paper, we'll see you in a week. Emily, it's been really nice. Good to see you again.
Yep, don't get sick.
I'll try my best not to. You too, listeners. We'll catch you soon. Bye.
Bye.